Dimensional analysis shows the relation of derived quantities to the fundamental quantities from which they are derived from. Now, take note that we have three main fundamental quantities from which we obtain the dimensions of other quantities. We have the mass, and the dimension of the mass is capital letter M. We have the length, whose dimension is capital letter L, and we have the time, whose dimension is what? Is capital letter T. These are the three main fundamental quantities from which we obtain the dimension of other quantities. Now, let's look at something. Look at area, for example. Area, the formula for area is, we always know that what it is, what length times breadth. Take note of something. You see length, breadth, height, altitude, distance, displacement, and so on like that. All these, anywhere you see them, the dimension of this quantity is what? Is L. All of them still represent what? Length in dimension. Don't forget that. So looking at all this, it means that the dimension of both length and breadth here is what? L and L. So I will say that what the dimension of this area is L times L, and that is what? L square. So that is the dimension for area. Then look at another problem. If I look at volume, area times height, and the dimension of volume will be what? If I'm using this bracket, I'm trying to say the dimension. Now let's go. Area has dimension of L square. Remember, height has the same dimension as length. So I'll say what? L raised to power 1. And this will give me L to the power of what? 3. And that's the dimension of what? Of volume. Let's look at another problem. Let us look at density. If I look at density, if you observe density, density represented as rho. The formula is what? Mass over volume. The dimension of mass has been written here, which is capital letter M. Let me write that in the next one. So the dimension of density will have to be capital letter M over dimension of volume is what? L cube. And I can write this as ml to the power of what? Negative 3. That is it. Let's go further. Let's look at velocity. You see, velocity, speed, these two has the same word, the same dimension. So dimension for speed is also same thing as dimension of what? Of velocity. So let's go. Look at speed, for example. The formula is distance over time. Remember that the dimension of distance is the same thing as that of what? As that of length. So I'll say L over T is time. The dimension is a capital letter T, then raised to power 1. So I'll have LT raised to power negative 1. That is it. All right. And that's the same dimension as what? As velocity. Okay, let's go on. Let's look at another quantity. Let us look at momentum. Momentum. The formula for this is mass times velocity. And the dimension of momentum here, dimension momentum is always represented as what? P. Dimension of momentum is, let's go, mass is capital letter M. Dimension of velocity, look at it here. Where is it? Speed of velocity, this is it. And that's what? LT minus 1. MLT minus 1. That's what? Dimension of momentum. And guys, take note of this, that the dimension of momentum is also the same thing as the dimension of what? Of impulse. Okay? So take note that what? They are equal in what? In dimension. And also note that what? The formula for impulse is what? Force times time. This will give us the same dimension as what? Mass times velocity. You can work that out. So let's go. Let's look at force. Or before force, let us look at acceleration. Now, acceleration, A. The formula is what? Velocity over time. And if I should look at this, what will be the dimension? You see, the dimension of AM of this acceleration will be equal to what? Check it out. V is velocity. And this is the dimension here. And that is what? L c minus 1. Then all over, look at this. This is time. And that's what? Over t. Don't be tempted to say t cancel t. It is wrong simply because this t here is having a power of -1, while this one is +1. So they won't cancel each other. Rather, this will come up and make it -2. Therefore, the dimension of acceleration will be equal to what? Lt minus 2, and that is it. All right, let's now look at dimension for force. Let's now look at dimension for force. F, which is equals to mass times acceleration. So the dimension of this, of force, will be equal to what? Check it out. Mass dimension is what? Capital letter M. And acceleration is what? Lt minus 2. And that is it. As simple as that. So let's look at surface tension. Let's look at surface tension. And the formula for surface tension is what? F over what? F over L. All right. So what will not be the dimension? Let me say this representing what? Surface tension. So what will not be the dimension of surface tension? That will give me what? Check it out. Force, the dimension is mLT minus 2 over length. I have length here. So this will take care of this. They are both positive, positive. So therefore, dimension of this is what? Sorry, that will be what? MT minus 2. All right. Let's look at another quantity. Coming. Okay, let's look at viscosity. Let's look at viscosity. And what's the formula for this? Is what? Force over area times velocity gradient. And that is just velocity over length. So let's go. Remember that this is what? The dimension of this. The dimension of force is what? M, L. The dimension of force is, I have MLT minus 2 over area is L square times velocity. We have done it before, and that is what? Lt minus 1. Then all over L is what? Is 1. This will take care of this, very sure. And also, this length here you have here, we also take care of one of these. So I'll be left with MC. Okay, now look at this part. Also, you can see that they are both having negative power. If you check, they are both having negative power. So just like I have t to the minus 1 times t to the minus 1, that will give me t to the minus 2. Then the denominator, I have t to the power of minus 1. So one of these will take care of one of these. So the thing is that this one will cancel one of these, then I'll be having t to the power of minus 1. So the dimension of viscosity I'll be having here now, the dimension of viscosity I'll be having here now will be, that will give me what? That's what? M. Then this is L. I just have only one L left, which is raised to power 1. So all over L to the power of 1. Then I have C to the power of what? Minus 1. Now check it out. When this one comes to the numerator, you'll be having raised to power minus 1. And this is to power minus 1. And that's the dimension of viscosity. So let's look at one more example. Okay, let's look at the dimension of pressure. Pressure is force over area. And if you look at the dimension of pressure, well, that's pressure, is what I have MLT minus 2, which is for the force, over area is L square. This will take care of this. So we're having the dimension to be equal to MT minus 2 over L to the power of 1. If I write that, I'll be having this. If you check it out, this, when it comes up, it becomes something like this. And that's dimension for what? For pressure. Okay, now let's take a simple test. And the test is this. This is a simple test. You can comment your answer below. If you are watching this video, you can comment your answer. Now, find the dimension of these quantities. Take this task. Find dimension of these quantities. Power, work, which also has the same dimension as energy. So, take note of those two. All right. So, I will erase this and solve more challenging problem. All right. Let's look at the dimension of gravitational constant. Gravitational constant, which is represented as a G. Now, take note of something. There is a particular law in physics we call the Newton's law of universal gravitation. And what does it state? That F is equals to G mm all over r squared. If I make this G the subject of the formula, I'll be having G equal Fr squared over mm. Now, from here, I can deduce that the formula for G is what? Fr squared all over mm. F is the force, R is representing distance. Okay. Also, if you are using a formula that also have radius, it will have the same dimension as length. All right. So Fr, force, radius, are both mass. So I can say the dimension of G will be equal to force. The dimension is mLT minus 2. We've done that previously. Times the dimension for this is L, then I'll put square all over. This one is m times m. They'll have the same dimension. Okay, so take note that this guy, we take care of this guy. So from here, I'll be having L raised to power 1 times L squared will give me L to the power of 3, then C to the power of minus 2, then all over what? M. So the dimension of gravitational constant is M to the power of 1. When it comes to the numerator, you'll be having M to the power of minus 1, L to the power of 3, then you have C to the power of what? Minus 2. That is it. All right, what is the dimension for this quantity? What dimension for electromotive force? Electromotive force. Okay, EMF. All right, take note that EMF is equal to work done all over charge. Now, what's the formula for work done? I can take this as first time distance traveled, then all over Q. Now, this electromotive force here, the dimension, take notes before that. Look at this. Look at this Q. This Q here has a formula. This Q is the charge. It has a formula, and that formula is what? IT. Now, current doesn't have dimension, so I'll replace it as I. So let's replace the dimension of all these quantities. So I'll have dimension of EMF to be equal to force is mLC minus 2, distance is L, current I'll replace it as I, then time is capital letter T. All right, nothing can cancel out, so I'll have M, L times L will give me L squared. Take note, this is to the power of positive 1. It will never cancel this. Don't make the mistake. Rather, it will come up to make it what? Minus 3. This is minus 2 already. When 1 comes up, it will become minus 3. Minus 3. Then I to the power of 1. When it comes up, I to the power of what? Minus 1. This is the dimension for what? Electromotive force. All right. Let's look at another quantity. Let's look at dimension for specific heat capacity. Specific heat capacity. Specific heat capacity, which is C. Take note that there's a formula we have to bear in mind, that Q equal MC change in theta. Okay, this is change in theta. Let me write that change in that delta theta. All right. If I make my C the solid of the formula, I'll be having Q over M change in theta. Take note that what this Q represents energy, right? This Q here that you are looking at here and this work done, we have the same dimension. Remember that work done and energy, we have the same dimension. So everything I've written here is the same thing as this Q. Okay, let me quickly work out the dimension of work done. So take note that our work done is force times distance. So the dimension of what? M L T minus 2. This is for force times this distance. This is own dimension. So I have M L squared C to the power of minus 2. So that you see, this dimension is for the work done. It is also the same thing as this what its energy here. So work done and energy have the same dimension. So I'll be replacing this and write M L squared C to the power of minus 2 all over, what is this M? M is the mass. And theta that you are seeing here is for the temperature. It has no unit, so I'll replace it as just theta. It has no dimension, just theta. So the dimension for this will now be equal to, what will I have here? I have M will take care of this M. So we left it what? L squared T minus 2, then theta raised to power. You know it's 1. When it comes up, it becomes minus 1. And that is the dimension. So that's that about that on finding dimensions. So let's proceed to the higher level. Let's proceed to the higher level. Now, take note of something. And that thing is that, what is the application of dimension? The thing is that what we use dimension to test what we call homogeneity, or we call it uniformity of equation, or we say the correctness of equation. We use it to test the homogeneity, uniformity, or the correctness of equation. Now, how do you know an equation is dimensionally correct? The principle is that the dimension of each quantities in the equation have to be equal. For example, if I have this equation now, A plus B equal to C. Let me say I have this equation now. Dimensionally, dimension of A must be equal to dimension of B and must be equal to the dimension of C. That the dimension of each quantities you have here must be the same. If they are not the same, then the equation is wrong. It is not dimensionally correct. All right, let's look at another one. If I have A equal BC plus DE, take note that dimension of A must be equal to dimension of BC and must be equal to dimension of DE. You can observe each of the quantities that you have here must have what? Must have the same dimension. And that is it. So if I have E equal MC square, dimension of E must be equal to dimension of MC square. And that is it. So that's what we call what? The principle of homogeneity, and that is it. So we'll be applying this. It's very important. So if you are asked to check whether an equation is correct, you have to find the dimension of each of the quantity. So if it is correct, then that equation is dimensionally correct. All right, we move. Okay, let's look at this. If we have T equal K M to the power of X, L to the power of Y, and G to the power of Z, this T represents the period of a simple pendulum, and it represented this way. We are asked to use the dimensional analysis to find the value of X, Y, and Z. Then put it back in the equation and we obtain the formula for the simple pendulum, for the period of the simple pendulum. Now, we have T equal Km to the power of X, L raised to power Y, G raised to power Z. K is a constant. This K is a constant. K is a constant. To be precise, a dimensionless constant. It does not have dimension. Okay, so what do we do? Let's solve. For this equation to be correct, remember the dimension of the left hand side must be equal to, this K doesn't have dimension, so I'll remove it. Must be equal to dimension of the right hand side. Good. So remember, T is period, and period is also time, but just different. But take note here that it is also time. So it will have the same dimension as time. So dimension of this period is just what? Capital letter T also equal, check it out. Mass, the dimension is capital letter M, then raised to power X, times L, the length, the dimension is L raised to power Y. Then G, look at it. Remember that previously I derived the dimension of A acceleration. Taking that the dimension of A acceleration is also the same thing as the dimension of acceleration due to gravity. The difference between this and this is that A is acceleration, while G is acceleration due to gravity. And that's it. So it will have the same dimension. So I'll say this has the same dimension as acceleration. So I'll have LT minus 2, then raised to the power of Z. So I'll have T equal M to the power of X times X to the power of Y times this. Observe in indices, if I have AB to the power of N, this is the same thing as A to the power of N, B to the power of N. So I'll separate this Z for both of them. So I'll be saying L to the power of Z times T raised to the power of this and this multiplies to give me minus 2Z. All right. So I'll say T equal M to the power of X. Law of indices. I have L. I'll pick one and add the powers together to be Y plus Z. Then I'll have T raised to power minus 2Z. Now take note of something here. Do you remember in mathematics that a number raised to power 0 equal to 1? And look at this left hand side. I can rewrite this left hand side as m to the power of 0, L to the power of 0, then T that is 0 raised to power 1. You observe that m raised to power 0 is 1, L raised to power 0 is 1. 1 times 1 is 1. 1 times T will still give me T. So it's like I'm not changing anything. I'm writing this because I want left hand side and right hand side to resemble one another. So I have m to the power of x, L to the power of y plus z, T raised to power minus 2z. Now I'll compare the powers on both sides. So comparing powers on both sides. What happens now? Let me compare the power of m. Comparing the power of m, what happened? Here I have x and it must be equal to the power that we have here, which is 0. Let me tell you the principle. Power of m here, you relate it to the power of m here. Power of L here, you relate it to the power of L here. And the power of T here, you relate it to the power of T here. And that is the principle. Okay, let's look at this. Observe, look at T here. Let me compare T. Look at T here. The power of T here is minus 2z and must be equal to the power of T here, which is 1. Therefore, if I divide both sides by minus 2, then I'll have z to be equal to what? 1 over minus 2. Or you can say minus 1 over 2, no problem. That's z. Then let's now compare y. Let's compare y. Y is to compare power of L. On the right hand side, I have y plus z, and that's equal to 0. I don't know why. My z is equals to minus 1 over 2, and that's equal to 0. Then y will be equal to 1 over 2. Now, check it out. By dimensional analysis, x is equals to 0, y is equals to 1 over 2, and z is equals to minus 1 over 2. Now, observe. All right, this is what I have. Now, observe something. We've gotten all this. So how can we now get the formula for the simple pendulum? Take it back to the equation. So recall to the original equation where you have T equal Km to the power of x now is now 0. Observe what you have here. X now is now 0. Y is now half. G is now minus half. So I have T equal K. Anything raised to power 0 is 1. So that will have no effect. G raised to power minus half. Now, when minus half, it is possible for you to come down the equation. So we turn it to g raised to power half. See, when I bring this to a denominator, this minus will disappear. Observe, this power is common to both of them. I can write it as k L over g, then put the power of half. I can still separate it back for both of them. So remember, anything raised to power half is square root. So therefore, I have t equal k square root of L over G. Now, it makes sense. So that is the final answer using dimensional analysis. And what can we deduce? We can deduce that the period of a simple pendulum do not depend on the mass of the bulb. You can see that after getting the real formula for the period of a simple pendulum, there is no mass in the equation. It means that the period is independent of the mass. All right. Let's look at another problem. You have F equal K R to the power of A, this power of B, and you have omega to the power of C. Now, how do we go about this? Take note that F is your force, this represents force, K represents a constant, R represents the radius, eta, this one you have here, represents the viscosity, and here represent what? The angular velocity. Represent what? The angular what? The angular velocity. So let's first get their dimension. Check it out. Remember that by the principle of homogeneity, the dimension of this must be equal to the dimension of, remove K is dimensionless, R to the power of A, N to the power of B, and omega to the power of C. So from here, what will I have? Dimension of F is what? MLC minus 2 equal radius. Dimension is L to the power of A. This is viscosity. Remember that previously we did dimension of viscosity and we got ML minus 1, C minus 1. So I'll put it there. ML minus 1, C minus 1, then to the power of what? B. And what is angular velocity? How do we get the dimension? It's nothing to panic about. Check. If I have omega, you know that, remember that this omega is equals to what? V over R. That is from circular motion, velocity over radius. Take note of that. And the dimension of this will be equal to what? What's dimension of velocity? LC minus 1. Dimension of radius is just L. So cancel it out. So the dimension of this here will be what? Will be 3 raised to power minus 1. Dimension of this is 3 raised to power minus 1. So I'll just write 3 raised to power minus 1. Then I have power of what? C. I believe you are following. Okay. Now we move. So I have MLC minus 2 equal, I have L to the power of A. This, if I expand, I have M to the power of B, L to the power of minus B, C to the power of minus B, then I have C to the power of here minus C. So I have MLC minus 2 to be equal, I only have one M here, so I write M to the power of B. Observe, L is here, and also L is here. So I'll combine them together to have L raised to power what? A minus B. Observe, you have A here, you have minus B here, so you combine together. And lastly, ML, then C is what? I have minus B here, and I have minus C here. So this is what I have. Comparing both sides, remember this power 1, this power 1. So comparing both what? Both sides. So what do we have? We have, if I compare the power of M, I'll have B to be equal to 1. If I compare the power of L, I'll have A minus B equal to 1. And if I compare the power of C, check it out. Before we even move, I can just get, check it out. A minus B is 1 here, then equal to 1. A will be equal to 1 plus 1, and A is 2. And if I compare the power of T, I'm having minus B minus C equal to minus 2. Observe, here and here equal. So, check it out. I have the value of B. I'm coming. The value of B here is 1. Then minus C equal minus 2. So therefore, minus C equal minus 2 plus 1. Minus C equal what? Minus 1, and C equal to what? 1. All right, that's interesting. So we can just cross-check our solution briefly. So A minus B equal 1. All right, that's that. So since we've gotten this, therefore, by dimension, we're able to find the value that what? That A is equal to 2, B is equal to 1, and C is equals to 1 by dimension, and you've gotten the values. That's just the instruction that you have to find A, B, and C. That does it. And if you're asked to find the main formula, you have to substitute everything you have here inside this what? Inside this equation. Okay, then you have F equal your K, R to the power of 2, R square, N, then C. That's that for that. Okay, let's look at another aspect of problem. Another aspect of problem is this. You have to check the correctness of this equation. Check the correctness of this equation. E equal mgh plus half mv square. Now remember the principle. What's the principle? By the principle of what? Homogeneity, the dimension of E must be equal to the dimension of what? Mgh, and must be equal to the dimension of what? Half mv square. All right. So let's see if this will be true. What's dimension? What is E? E represents energy. Okay. E represents what? Energy in this equation. You will have been given in the question what each of them represents. E represents energy. And take note, the dimension of energy is the same as that of work done, and that's ml squared t raised to power minus 2. When you practice very well, of course, this will go stuck to your memory. Next, let's look at this. What's dimension of mgh? Let's go. This is capital letter M. This is acceleration due to gravity, is LT minus 2. And this is height, which is L. Multiplying together, I'll have ml squared t raised to power minus 2. Also, I have half mv squared. But remember, you won't include the half in the dimension because half is dimensionless. Numbers are dimension. Numbers like pi, e, numbers that you have, they are all what? They are all dimensionless. All right. So what's dimension for m? Capital letter M. Velocity is what? Lt minus 1. Then I have this power 2. So if I expand the power, I'll have L square, this minus 2, because this square will multiply this, L square, this multiply this minus 2. And you can see dimension, you can see that what the equation is dimensionally correct because dimension of this is equal to the dimension of this and also equal to the dimension of what? This. And that is what? And that's correct. So take this task. I can comment your answer. The task is this. Check the correctness of this equation. V equal square root of E over D, where your E represents the Young modulus and D represents what? The density. Or yeah, E represents Young modulus. And remember, Young modulus is stress over strain. Let me give you hints. Your Young modulus is what? Stress over what? Over strain. This strain does not have dimension, it's dimensionless. So, and this stress has the same dimension as pressure that I've done before. So the gist is just that dimension of this will be equal to dimension of everything you have here. Then you work it out. So that is the end of today's lecture on dimension. So like the video, comment, and if there's any ambiguity you don't get, put it in the comment section. Thanks for watching. Bye.